All right, so for section 9.3, this would be actually quite simple for you because it's basically the same idea as what you did with 9.2 with proportions, but now we're just doing averages, we're doing the mean. So remember, there is a key difference between the proportions and the means, and that is the particular test statistic that you're calculating, whether it's Z or T. So remember, when we do not know the population standard deviation, we have to use the sample standard deviation, which we know as standard error. And when we do that, we have to use the t-distribution. So we're going to do this lesson in 2 videos. One video is going to be the first 4 learning targets here, stating and checking our conditions, calculating the test statistic and the p-value, performing the test, and then use a confidence interval to make a conclusion for a 2-sided test. A separate video is going to be on the power of a test. All right, so when you're carrying out your significance test, remember your conditions. You have that the data must be a random sample. You have your 10% condition, that your sample is less than 10% of your population. And then for your large sample for means, we're looking at whether the population distribution is normal or if our sample size is greater than or equal to 30. If neither one of those are correct or known, then the last thing you can do is provide a graph of the sample data and see if it's normal. Now, whenever you are showing whether your sample data is normal, you can't just put it in your calculator and be like, oh, it's normal. Remember, we have to provide a sketch on our graph or on our paper, whether that's a box plot, a dot plot, a histogram. But remember, it's a sketch. You don't have to sit there and make sure your scale is perfect and things like that. It is a rough sketch. All right, so here we have the lifetime of the batteries. I know we've done this one before, or at least talked about it at the beginning. So here are the lifetimes of 15 deluxe AAA batteries from the company's Simple Random Sample. Check if the conditions for performing the significance test are met. Well, it already says that it's a random sample of 15 deluxe AAA batteries. We can assume that 15 is definitely less than 10% of all the batteries that the company creates. And then we do not know the population distribution shape, and 15 is less than 30. So the only way to check for normality is to look at a graph of the sample data. So they provided a dot plot here. And remember, you're just looking for any signs of strong skewedness or outliers, which are not present here. So all the conditions check out for this example. All right, so whenever you start carrying out the test, remember you have your test statistic is equal to the statistic, the sample value, minus the parameter value, the population value, divided by the standard deviation. So when you put that all into your symbols, if you know the standard deviation of the population, that's the ideal situation, then you're using Z. Z is equal to X bar minus the mean over sigma divided by the square root of n. But if we know what sigma is, the standard deviation, then we know what the average is. So that's not realistic. So that's why we have to use our t-distribution. So our t-distribution is based on the fact that we do not know the population standard deviation, and so we're using standard error. Again, we did this in chapter 8 when we were doing confidence intervals. So this is not really new information. We're just using it in a different setting now. All right, the other part was we introduced degrees of freedom whenever we were using the t-distribution. And degrees of freedom is the sample size minus 1. So we also talked about the t-distribution has more area in the tails of the distribution in comparison to the normal distribution. So you do have a different chart that you're looking at, and it also means you have a different program in your calculator that you're using. All right, so as your degrees of freedom increases from here 2 to 9, you see that this graph from your 2 degrees of freedom to 9 to your standard normal curve, that the larger your sample, the more normal, I guess you could say, the graph looks. Now, these are all normal distributions, so what I mean is it's becoming the standard normal curve. All right, so in order to find your p-value, that probability, you're going to use table B, your t-table. So when we were in class, the t-table was on one side of the sheet, and then we had a different distribution on the other side. We're not going to be using that other distribution, the chi-squared test, because that's one of the units that has been taken away from the AP exam this year. So if we're talking about the batteries, the idea was that the standard normal AAA batteries that they produced, their average lifespan was 30 hours. And these new AAA batteries are supposed to last longer. So that's what your alternative hypothesis is. So based on the data that was given, the average of the sample was 33.93 minus our claim is that it's still just 30, divided by, you have your standard error, that's the sample standard deviation, then divided by the square root of n, so 9.82 divided by the square root of 15, that gives us 1.55, and so our degrees of freedom would be 14. So, going to your table of values, you have here, remember, you go first to your degrees of freedom, which here's 14, and then you go across the table and you're looking for 1.55. So 1.55 is between these two, between 0.10 and 0.05. So that means our p-value is greater than 0.05, which is our standard alpha value. Okay, so that's the one thing about using the table is we have limitations. We're going to get most of the time we're going to get an interval for what the p-value could possibly be. Okay, so you get an interval of plausible values. It's only going to give you for positive t-values. So if you get a negative t statistic, just treat it as a positive to go in your table and find it. Also, on your table, it skips a bunch of values for the possible degrees of freedom. So remember, whatever your degrees of freedom are, then you look for that number or the number closest to it that is less than it. So for instance, it tells us here that it skips degrees of freedom to 40, 50, 60, 80, 100, and 1,000. So if our degrees of freedom was 78, then we would use 60. Now again, this is coming from the table. If you're in your calculator, it'll use degrees of freedom of 78. Okay. All right, so suppose we want to perform this test where the claim is equal to 5 versus the alternative is not equal to 5 at the alpha is 0.01 significance level. So we have a sample of 37, x bar is 4.81, and then the sample standard deviation is 0.365. Assume the conditions are met, so we just want to know what ends up happening for our test. Do we reject or do we fail to reject? So explain why the sample gives us some evidence for the alternative. Well, the alternative says that it's not equal to 5. We look at our sample, we have 4.81. Well, that's not equal to 5, so it suggests that the alternative may be true. So part B is actually calculating the test statistic and p-value. Okay, so part B, here's kind of a visual of what's going on whenever you standardize everything. Okay, so t is equal to 4.81 minus 5 divided by 0.365 over the square root of 37. This gives us a negative 3.17. And our degrees of freedom is, again, the sample size minus 1, so we get 36. So in our table, we go along. 36 is not on there, so we use 30. And now we're going to get a p-value between, looking up here, between 0.001 and 0.0025. Okay. Now, that's just looking at greater than. Our hypothesis test here is saying not equal. Remember, this is called a two-tailed test. Because we're worried about not just greater than, not just less than, but both scenarios. So when you find that p-value, you then have to multiply it by 2 to get the true value. So multiplying both of those values by 2, we get 0.002 and 0.005. So that means the final p-value of this hypothesis test is between 0.002 and 0.005. Okay. Now again, using the table, we're going to be very limited on the values that it gives us. It's going to give us a range. So you can use your calculator. All right, so when you use your calculator, you have a choice here on what test you're using. You have a one sample Z test and a one sample T test. Z is used whenever you have the population standard deviation, which is hardly ever. T is when you have the sample standard deviation, which is majority of the time. So in order to use that particular test on your calculator, you go to Menu, Stats, Stat Test, and you go to Z or T test. It's one of the very first options. It does not say for means like the proportion one did. So I think Z test is the very first option, T test is the second option. So you're going to do your T test and you can put in the statistics or the data. Again, you've gone through that before. So when we do that, when we're looking at for T being greater than 3.17, we get a value of 0.001554. If we're looking at greater than 3.17 or less than negative 3.17, we can take that 0.00154 and multiply by 2, or we can tell our calculator to find it one time and multiply by 2 so that we get the final p-value of 0.0031. Remember, it was supposed to be between 0.002 and 0.005. And so our final p-value from our calculator gives us the exact p-value, which is in that interval. All right, so when you're doing the entire thing, remember you have 4 things to do. You have to state your hypothesis and your significance level, and then define the parameter. What does mu stand for? Identify the appropriate inference method and check the conditions. This is where you will say a one sample t-test for population mean. Then, after you've shown the conditions are met, you'll perform calculations. You'll give the sample statistic, you'll calculate the standardized test statistic, and you find the p-value. Also, be sure to list the degrees of freedom. It's not stated right here, but I would definitely do that. Then you conclude by making your conclusion about the hypothesis. Do we reject or do we fail to reject? So remember, all those conditions that we have to check are different parts of your overall formula. So number 1 was the random condition. That helps to make sure that x bar minus the claimed average is a good estimate for the difference between the actual true value. The large count condition is what allows us to use the t-distribution, that something is approximately normal. And the 10% condition is helping us to do the standard deviation. So here's just kind of your overall view of all of what you're doing, your formula, and then the 3 situations that it could be a one-tail or a two-tail test. Now, going through an entire thing, this is about oxygen levels. So do the data provide convincing evidence? It tells you the alpha value. All right, so do the data provide convincing evidence? So we want to test whether mu is equal to 5, mu is less than 5, where mu is the true mean dissolved oxygen level, using alpha as 0.05. It's a random sample. We can assume the 10% condition. Here's a graph of the data. See, here's a histogram situation. It's practically symmetric, and there are no outliers. Right? We have our sample value, our sample standard deviation. So t is negative 0.94, degrees of freedom are 14. So using the table, you get a p-value between 0.15 and 0.20. Using your calculator, it's 0.1816. Now compare the p-value to alpha. The p-value is greater than alpha, 0.1816 is greater than 0.05. Therefore, we reject HO. We do not have convincing evidence the true mean level in the stream is less than 5. So part B, it says, given your conclusion in part A, which kind of mistake, type 1 or type 2 error, could have been made? Explain what this mistake would mean in context. So because we failed to reject it, we could have made a type 2 error, meaning that the alternative was actually true. If we did, then the true mean dissolved oxygen level in the stream is less than 5, but we didn't find convincing evidence in our significance test. This would imply aquatic life in the stream is at risk, but we weren't able to detect that fact. So, those of you that are using your calculator, which I know majority of you are, you need to be very careful that you're going to get credit for the do step of the process. So, when you're using your calculator, make sure you name the procedure, so that'd be a one sample t-test for means, and you report the test statistic, that's t, the degrees of freedom, and the p-value. If you provide that information, then you're going to receive full credit for the question. So, two-sided tests and confidence intervals. Remember, hypothesis testing and confidence intervals are related, but it's only when the significance test is two-sided, okay? A 95% confidence interval for mean does not capture the null when we reject the null on a hypothesis test at the 0.05. The 95 and the 0.05 together, that's 100%. So that's kind of how these work. They're complements of each other, and so they go hand in hand. So if a 95% confidence interval does capture the null, then our significance test would have said we failed to reject. The same logic applies for other confidence levels, right? So if it's an 80% confidence level, then alpha is 0.2. It all has to add to 100. But again, it's only for two-sided tests. So we could work out this next problem and it'd be the same thing. Stating your hypotheses, checking your conditions. Part C here, it gives us the actual confidence interval of 95%. And then you would then compare between the significance test and the confidence level. So here I'm going to go, part C was doing the confidence interval does not include 31, so we reject the claim. We have convincing evidence that the true mean weight of all pineapples grown this year is not 31 ounces. And then, can we conclude that the different irrigation system caused a change in the mean weight? Explain. No, because it wasn't a randomized comparative experiment. Random is a key component to being able to infer things for the population.